So, okay, so let's start. So let's just quickly recap what we have been seeing in the last couple of classes. So we started with this basic pipeline architecture, and we started to look at what all can go wrong in each of these blocks and the way in which we can tackle these problems. So first we started with the problems with the ADC, and this essentially boils down to the fact that you will have errors in the transition voltage of the comparators. And we saw this results in the quantization noise becoming exceeding the limits of plus or minus delta by 2. And this can in turn saturate the succeeding ADCs when you use the full gain. So what was the solution to this problem? Right, so we reduce the gain. So we have one extra bit of redundancy that seemed to solve this issue. So we moved on and looked at the issue in amplifier. So first was, oops, it's taking a lot of time to load. Okay. Yeah, okay. So yeah, so then first we looked at the offset issue, and we saw that, the offset in the first amplifier just adds to the overall offset of the ADC. So this offset doesn't create a big issue, right? And the offsets on the succeeding stages get divided by gain that is seen before. The only thing to be careful is you need to make sure that this offset is not so large that it can saturate the next ADC, right? Because the input to the next ADC is this gain times this quantization noise plus offset, right? And in most cases, since we are already using a smaller gain here, this might not be a problem. So then we looked at what can happen with the gain error. That is, what happens if the gain we have for this residue amplifier is not the exact value we want. And we saw that this results in the quantization noise of the first few stages, or in this case, the first stage, getting leaked to the output. And of course, this can be corrected either by fixing the gain in the analog domain itself, or a more common or a more easier solution is to fix it in the digital domain, where you make sure that the digital gain you have here matches the analog gain you realize. Okay. And then before looking at the non-idealities in the DAC, we decided to look at how the circuit is actually implemented so that we can have an understanding of how the DAC is actually realized. And we knew how to realize the flash ADC. So the only remaining part is this portion which I'm highlighting. And it turns out that this boils down to realizing a simple switched capacitor amplifier like this, right? So we saw that the DAC, in turn, the output must look like this. That is the V1 minus V1 bar times Vref by 4. Right? In 2-bit case, Vref by 4 is, how is Vref by 4 related to the step size for a 2-bit case? Sorry? This is we have considered a 2-bit example, right? So in that case, I told that the DAC must have produce an output of this form. That is V1 minus V1 bar times Vref by 4, right? So how is this Vref by 4 related to the step size of the 2-bit quantizer? Sorry? Delta or delta by 2? Delta by 2. Okay. Right. So so essentially it turns out that this input minus the DAC output turns out to be of this form, right? And for the 2-bit ADC, we wanted a gain of 2. So this is what we want to have at the amplifier output. And this portion in turn was rewritten slightly like this, right? So where I multiplied and divided by 4, and I rewrote the output you want in this format, right? So we now have 4 such inputs to be amplified, and each needs to have a scaling factor of half. So this boils down to having 4 such switched capacitor branches, right? So the first 3 will have the controls of the DAC, and the last one will just be grounded because we don't need to have the DAC. Okay, and sorry. And since we wanted we wanted a gain of 2, right? And this gain is split into 4 parts like this, and each part needs to have a gain of 1/2, right? And that is why the capacitors we chose were of this form, where if the feedback capacitor is C, these are C by 2. Okay. And finally, we looked at how the timing is, how the various stages operate in different phases. So the assumption was the first ADC samples in phi 1. So it produces the output during phi 2. So during this phase, the residue amplifier will take this and amplify it, and the output is ready during phi 2. So the second ADC can sample it during the same phase. Okay. So which means in the next half cycle, which is the next phi 1, the second ADC produces its output, right? Similarly, since the second ADC has the output ready in this phase, the second amplifier, which has to amplify the error produced by the second ADC, will finish the amplification in this phase itself. So the third ADC can start sampling during this phase. So it will produce the output in the next half cycle, right? And the sequence keeps repeating. Okay. So we find that the outputs of the individual ADCs, they are staggered by half clock cycle. So before you do the recombination of something like this, G1, G2, you need to make sure that all these are time aligned. That's all, right? And now, although we saw the circuit for only a single-ended version, for the differential version, you just have the same replica. Let me show the circuit. So the same portion we have will come in the other half also, right? Only the inputs will be differential. This positive input becomes negative input. Similarly, the DAC controls will change the polarity. That's all. V1 will become V1 bar, and V1 bar will become V. So now, okay, let's look at the circuit again. So this is in particular for a 2-bit case, right? When the front-end ADC is a 2-bit ADC. Now, by looking at this, can you tell me how many such switch capacitor branches will be there if the front-end ADC was a 3-bit ADC? How many? Sorry? 8. Why 8? So, I mean, look at it here, right? So the first 3 branches take the input as well as the DAC, right? And the DAC has how many inputs now? How many bits are there for the input of the DAC? I mean, ADC output is essentially the DAC input, isn't it? So for a 2-bit case, how many, I mean, remember ADC output is in the thermometer port format. Sorry? Correct. These are directly feeding here. Correct. Okay. 8. Okay. So here we have 3 stages. I mean 3 branches, and these 3 take the DAC input, and 1 additional branch for the input alone. Similarly, for the 3-bit case, you'll have 7 output bits, right? 7 comparator. I mean 7 thermometer output bits. So we'll have 7 such branches, and 1 additional branch for the input. And what do you think will be the capacitor values in these 7 branches, assuming that this capacitor is C? Sorry? No, I'm talking about this capacitor values here. If this is C, okay, okay. So for a 3-bit ADC, what will be the gain you want to realize actually? 4. And this gain is split into how many branches? 8 branches. So each branch should have a gain of half. Is that okay? I mean, you can take the same and rewrite also, you'll get the same, right? So here I'm multiplying, dividing by 4. right? And had only 3. But for a 3-bit ADC, you'll have 7 such thermometer bits, right? So we'll multiply and divide by 8. Okay. And the gain here, let me write. So you'll have multiply and divide by 8. And the gain you want is 4. Okay. So the gain for the individual branch will still be half. Is that okay? I mean, the easier way to think is the overall gain you want is 4. That gain of 4 is split into 8 branches. So each branch will have the gain of half. So the capacitor values will still remain C by 2. Okay. The only difference is, so let me quickly draw. So we'll have branch 1, branch 2, and so on. So we'll have 8 such branches. So this will take the input and the DAC. So I'll say V1 of 6. You'll have 7 such things. And for the last one, you'll have only the input, nothing from the DAC. And the capacitor for each of these branches will be C by 2. Okay. And all of this will go to the feedback capacitor. That's fine. Any confusions or doubts in this? Okay. So now that we know how this residue amplifier is realized along with the DAC, let's look at the circuit once again and try to see where all the error in the gain can come from, right? So remember, overall we wanted a gain of 2 in this case, and each branch has to realize a gain of half, right? But we saw that, I mean, so what do you think can go wrong in this procedure? Yeah. Correct. Okay, yeah. This needs to be, yeah, correct. True. Okay, I mean, the point is we always make sure that the clock phases don't overlap. That much we ensure, right? So assume that is not a problem. Okay, I mean, the problem is if you exactly have 50% duty cycle like this. So if this is phi1, when you generate phi1 bar, there will be some delay from the inverter. So, and this can be a disaster because now you see that both these phases, which should have been exactly opposite, are active. So that's why, if you remember, we made sure that we don't have a 50% duty cycle. We have something like this. So assume that is fine. That's not a problem. The question is, we told that each branch needs to realize a gain of 1/2. I'm asking what are the possible things that can go wrong in this circuit that prevents us from exactly realizing the required gain. Capacitor value mismatch, right? First thing is that because this entire thing assumes the fact, I mean, it's based on the fact that this capacitor and this capacitor are ratioed in 1:2, right? So definitely capacitor mismatch is one. What is the other thing that you can think of? Sorry? Okay, op-amp offset, let's say that's a different thing, right? We talked about op-amp offset and how that affects, right? This is only about realizing the required gain. Okay, assume that switches are all ideal. Okay, so what are the other blocks that are remaining? One is capacitor, which you already addressed, right? Capacitor mismatch is mentioned. So what is the other block that is there? Sorry? Op-amp gain, right? So what do you mean by op-amp gain? Can you elaborate? Right. This entire thing assumes the fact that this is a virtual ground. So which means, so let me quickly draw one circuit to explain it. So if you had a case like this, so if the capacitor had a charge initially, we assume that when we connect it like this is virtual ground, this is also hard ground. So the entire charge in the capacitor will get transferred to the feedback capacitor. And that is when we'll get the exact gain of whatever you want, right? But if the op-amp has finite gain, that's not going to happen. Okay, so the gain error can come from two things. One is the capacitor mismatch, and other is the finite DC gain of op amp. Okay, and of course we saw if we don't realize the exact gain, we can correct it digitally, right? That we saw last class. So by the same token, can you look at the circuit and tell me for the DAC what all can go wrong? Again, remember that the DAC is this portion, right? So it takes each digital bit and switches one of the references, either 0 or VREF, and that charges the capacitor here, and the charge is transferred to the feedback capacitor. That's how DAC is functioning, right? It converts its bits to an equivalent voltage at the output, right? So now can you tell me what all can go wrong in the DAC implementation? I mean, again, remember that for the DAC we have 3 inputs, right? So let's say in this case it is 3, V1 of 3, V1 of 2, V1 of 1. Okay, we want an output of this form times some VREF by 4 or some voltage, I'll say, some V0, right? This is the expected DAC output. Okay, and this is again realized by having these 3 capacitors, and the 3 capacitors will have a charge corresponding to, let me draw it here. So here I'll draw. So each capacitor will have a charge corresponding to this, right? V1 of 2 times some C by 2, C by 2. Okay, and all of them are getting transferred to the feedback capacitor. That's how we are realizing this operation of V1 plus V2 plus V3 into some voltage, whatever. That's okay. So from this, can you tell me what can go wrong? I mean, ideally, what you want the 3 bits to be added with the same weight. Okay, is that clear? We want to just sum up these 3, and corresponding to their weights, we provide a voltage. Okay, and this is realized by having 3 different charges in 3 different switch capacitor branches, and then we are summing up these 3 charges in the feedback capacitor. Right? So first thing is, we assume that the capacitors are all equal, isn't it? If the capacitors are not equal, then we are not realizing this operation, isn't it? Okay. So capacitor mismatch is one major problem for the DAC. So for the DAC, this cap mismatch is one major issue because of the following reason. So ideally, I can mention, for let's say we have these 4 codes, 0, 1, 2, 3. So for code 0, I'll write the bits also. For code 0, all these 3 bits are 0. So ideally we want 0 volts. For code 1, we just want some voltage V0, right? Code 2, 2 V0, and code 3 V0. This is what we want ideally. Okay. And if you plot the input output characteristics of the DAC, where in the x-axis I'm plotting the code. So this is 0, 3. So I'll have a straight line, right? So for code 0, I'll have 0. Code 1, I'll have V0. Code 2, 2 V0, 3 V0. So I'll have something like this. Okay. I'll have a proper linear relation. Okay. But now if there is a mismatch in the capacitor, can you comment on these voltages? Sorry. Yeah, so let us say if this is 0, I mean, because you're not transferring anything, so this will be 0. So this ideally it should have been V0, but now this will be V0 into some 1 plus alpha 1 or something. Okay. Similarly, this will be V0 into, sorry, 2 V0 into 1 plus some alpha 2. Right? Is that okay? right? Because remember that this is the final output we realize, right? And each of these C1, C2, C3, ideally their values must be equal to some C0. But in practice, C1 will be some C0 plus delta C1, C2 will be C0 plus delta C2, C3 will be some C3 plus delta C3, right? So when you put these values here, you will find that along with the required voltages of V0, 2V0 and 3V0, that is coming from these capacitors C0, we also have an error voltage. Is that clear? Okay. So now if I try to plot it in this graph, it will look something like this, right? It might have any random voltages, right? Okay. So now this is having some kind of relation like this, right? So this is definitely a nonlinear operation. So this will straight away introduce nonlinearity. Okay, so this is a very big problem if you have capacitor mismatch for the DAC. And again, there are two ways to correct for it. You can go back and try to make sure the capacitor values are matched by doing some techniques. Or the other option is what? I mean, from whatever we have been seeing, how do you think we'll try to correct it now? Digitally, right? I mean, one is to try to correct the analog design, and that's going to be cumbersome. So we'll try to do it digitally. So let's see how we can do that. Yeah, you can do that, but still there will be some error. Okay, I'm not even talking about mismatches in the layout. The moment you have two different capacitors, you can have matching only to some level. Okay, so 0.1 to 1% you can get, and this will happen only if you have good layout technique also. If you make sure that you have lay the capacitors using proper techniques, then you can make sure that the matching between these capacitors can be of this order, 0.1 to 1%. But let us say you're targeting like very precise ADC where this is not tolerable, then you are having issues. Okay. No, we are giving the same voltage, right? In the sense, for each of the branches in the switch capacitor network, the voltages are same. Right? Yeah, I just took some example. It could will be that all of them are below the curve. In the sense, I could have had a case where everything is like this, right? Is that your question or something else? Yeah, we are getting. Sorry, I didn't follow. Can you repeat once? Voltage dependent, depending on which voltage you are talking now. No, this is the output of the DAC, isn't it? So input. Okay, this is dependent only on the capacitor values. See, if I have to show, I'll just have two branches. Okay. Ideally, let us say both the capacitors will be equal. So in that case, both the capacitors will transfer the charge to the feedback capacitor, right? So let's say this is some CF. And what will be the total charge that is transferred to CF now? No, I mean individually, right? So Vref times C1 plus Vref times C2, right? So the voltage you are realizing is Vref times C1 plus C2. That's the charge that is getting transferred. Okay. Now, if you just had one of the branches on, you will have only Vref times C1, right? For example, the code is 1, so that this branch is grounded. Okay, I mean, depending on the DAC code, you will switch this voltage to Vref for ground, right? So let us say the code is 1, that is only one branch is active. So in that case, you are transferring a charge, Vref times C1. If the code is 2, this is for code 1. For core 2, it is Vref times C1 plus C2, right? Okay, so this is only dependent on the capacitor values. I mean, of course, this is a charge that is transferred to CF, so the voltage will be this by CF, right? Is that okay? Okay, so let's see how we can correct for this digitally. For that, let's look at the two-stage pipeline ADC again. So let's say this is V1. This is the DAC. Say this is some G1. And you have second ADC here. And ideally, how do you combine the two outputs V1, V2? Sorry, V2 by G. Okay. So now, if the input is U, and let us say the DAC is functioning ideally, right? There is no problem. So the output of the DAC is a faithful reproduction of V1. Okay. So what is the input here? Sorry. Okay. Let's now talk. I mean, let's now talk only in terms of the input and V1. U minus V1, right? So this will be G1 times U minus V1. So V2 will be the input, which is this plus quantization noise of that ADC. So if you plug, if you put the expressions here, what you get? G1 times U minus V1 plus Q2. So that is V2, right? Divided by G1. And this is what finally you get, right? So this minus V1 and plus V1 cancel each other. Okay. And please remember that the output of the ADC is not actually V1. It is at 3 thermometer bits, right? So what we get is this, say V1 of 1, V1 of 2, V1 of 3. And how do we generate V1 from these 3 bits? Sorry, we simply add, right? That's how we convert the thermometer to the equivalent decimal or binary representation. So ideally, this is what V1 must have been. Okay. So I'll write that here also. So the same thing, V is V1 plus V2 by G1. And V1 itself, I'm writing it like this. Okay. And once again, I want to highlight that this is what we are doing from the ADC output, right? We are taking, I mean, we'll get 3 bits from the first ADC. We are summing the 3 bits like this to generate this V1. Okay. And now, let us say the DAC has capacitor mismatch. Can you comment on this signal? What will be the output of the DAC? Or you'll have, say, V1 hat. Sorry? That will come, right? So it just V1 of 1 into some 1 plus alpha 1. So V1 of 2 into 1 plus alpha 2 plus V1 of 3 into 1 plus alpha 3. Okay. And remember, this signal is what is going to the amplifier here. Okay. So here I'll have, sorry, right here V2, and V2 simply this fellow, right? The input minus the output that is produced by the DAC, which I'm now calling V1 hat. Okay. So this is going to be G1 times the input minus 1 plus alpha 1 V1 plus blah blah blah. Okay. Or let me write it also, 1 plus alpha 2. Okay. This is the input plus the quantization noise by G1. Is that okay? What I am doing is, instead of having this V1, I'm saying that the output is now, I mean, the input to the amplifier is V1 hat. That is the DAC output. And the DAC output is this, right? So here, instead of substituting V1, I'm substituting V1 hat. That's all. Is that okay? So now, okay, let me copy it somewhere. Huh? No, that's what we have considered, isn't it? After considering mismatch, we have this 1 plus alpha 1, 1 plus alpha 2, 1 plus alpha 3. Which mismatch are you talking about? Correct. This one? Correct, yeah. Yeah. No, see, that's what I'm trying to say. This V1, this is the output we are taking from the ADC, right? The ADC is giving 3 bits, right? And you are considering the equivalent decimal representation as sum of the 3 bits, right? This is what you are doing, but the DAC is not following what you are doing, right? It is doing something else, and it is saying that my output is this. Is that clear? So because of this, you see that now, I mean, ideally, if alpha 1, alpha 2, alpha 3 are all 0, so this term will exactly cancel this. Right? And we want this. Okay. The moment you have this find alpha 1, alpha 2, alpha 3, you see that this is not getting cancelled, and this is what is going to introduce nonlinearity. So now looking at this, can you tell me what can be done to cancel this? And recollect that the only outputs we have are the 3 bits from the first ADC and the second ADC output also. So let me write that once again. So what we have is V1 of 1 plus V1 of 3. And this is how we are reconstructing the first ADC output. Right? And the other portion that is coming from the amplifier is input minus 1 plus alpha 1 V1 of 1, alpha 2 V1 of 2, 3 plus Q2 by G1. That's fine. So let me just simplify it. I'll just cancel G1 from these two. So I'll just have this. Okay. Again, ideally, if alpha 1, alpha 2, alpha 3 are all 0, this portion will exactly cancel this. We'll not have issues. So now looking at this expression, can you tell me what you can do so that you can cancel this error terms? Sorry. And again, remember that the only outputs we have are the 3 outputs, V1, V2, V3. Okay. These are the 3 bits we are taking. Okay. Now, can you tell me what you can do to cancel this? Sorry. No, alpha is not under your control. Let us say alpha is something. Sorry. Huh? Copy of what? I didn't get you, but let's say you don't want to change the design. Let's say you design the ADC, pipeline ADC. This is the output you get, right? And I want to correct it now just by looking at, I mean, just by processing the digital bits. Right, that's all. In principle, what you have to do is, these are the 3 bits you are taking from the first ADC, right? What you are doing is you are saying that my output is sum of these 3 bits. But the DAC is not doing that. It is doing something else. So you do exactly what the DAC is doing. DAC is not following you, so you better follow the DAC. That's all. Okay. So instead of saying my output is this, right, and this is V1, right? Remember, I will say now my V1 is some 1 plus alpha 1 V1 of 1. Okay, is that okay? Now, if you do that, this completely gets cancelled, right? So normally what you would have done, you would have taken, no, we are not feeding anything to the DAC. Remember, yeah, the inputs to the DAC are, let me draw it maybe differently, the 3 bits, right? The 3 bits go to the DAC. right? You are taking the 3 bits out and you are doing the processing outside, right? These are the 3 bits, V1 of 1, V1 of 2, V1 of 3. Is that okay? So normally you would have done this, right? You would have taken the 3 bits and directly added it to get P1. But now what you have to do, you have to scale each of the bits by some gain. And then you have to add them. This is now my V1. Okay. And of course, earlier when you just had 3 thermometer codes, if you add them, how many bits you will have at the output? If you're adding 3 bits, what will be the? No, your thermometer has 3 bit output, right? So summing up these 3 bits. So the output, the binary representation will have how many bits? 2 bits. Okay. But now you are not directly adding the 3 bits. You are multiplying by some gain and adding it. So the output will have more than 2 bits, right? Because now you don't want 0, 1, 2, 3, you want some 1.01, 2.03 something, right? Because we want this 1 plus alpha 1, 1 plus alpha 2, 1 plus alpha 3. So the output will no longer have 2 bits, you'll have more than 2 bits. So you'll have say x1, x2, and then some say x4, x4, something like this. Correct. Right. Correct. It doesn't change a lot with the aging. The point is how aging is like a very long term, right? Like you're talking about 5-10 years. The point is, as you mentioned, for each device, this mismatch is going to be different. So for each ADC, you'll have to do it separately. Yeah, I'm not saying how you are doing it, but in principle, this is what you do. And how you find alpha 1, alpha 2, alpha 3, that is up to you. There are multiple ways. You can put your brain in. Bits, right? 0, 1, digital bits. This is digital gain. Something like that, yeah. Yeah, that again, that's based on how you are representing numbers. So for example, earlier, let's say I had 0, 0, 0, 1. After summing up these 3 bits, I mean, summing up the 3 thermometer bits, I'll have this as the output, right? But now I am saying I'll multiply each of the bits with something and then add. Okay. So I'll have more bits at the output. Say I'll say x1, x2, x3. So I'll say that this is my decimal point. So this is my, let's say 0, 0, 0, 1, 1, 0, 1, 1. On top of it, to correct for the errors, I am adding these extra bits. That's all. Something. Okay. So again, you can think of this as some kind of a redundancy. You are having redundant bits in the output so that you can correct for any errors you are making in the amplifier design. Sorry, in the DAC design here. Is that okay? And of course, this is not the only way in which you can correct for the DAC errors. There are other ways also, but this is one, say, common way. Okay. So one more thing I want to discuss. Sorry. Okay. So let's look at. So what I told here is earlier you just had the 3 bits. You directly sum them up. So the output you have only 2 bits, right? Right. No, the point is alpha. It depends on how much you want to match alpha, alpha to alpha 3, right? See, ideally, exact value of alpha 1 can be, let's say, 0.0005 or something. It depends on how much accurate you want to match in digital, right? I can say this approximately 0.004 also, or let's say 0.004 like this, or I can have one more bit and do this order. So the more number of bits you allocate, the more closer you will match the actual alpha 1, alpha 2, alpha 3. And of course, you can't exactly cancel it. All you do is you try to minimize it. That's all. That's all. No, we are not tuning the DAC, remember. Digitally we are doing, that is not controlling the DAC at all, right? So let me draw it here also. So these are the 3 bits that you are taking out. The DAC is simply taking the 3 bits and doing something and producing something here. What you are doing is you are trying to match what this DAC is doing. And that's why you are having these gains and then adding. So whatever you are doing here is not affecting the DAC operation at all. The point is ideally these two, whatever you are doing with these 3 bits and whatever the DAC is doing with these 3 bits, they should exactly match. Yeah, these are essentially correction factors. So, okay. So one last thing, say we have a 2-stage pipeline. And let us say the ADC here samples it or samples the input during phi 1. So in which phase did we say the residue amplifier must sample the input? Sorry? No, remember why phi 2? Yeah, amplifying in phi 2, but you have to sample exactly in phi 1, right? Because this is the clock to the ADC, or let's say this is the clock phi 1. And say your input is varying like this. The ADC is sampling these voltages and producing a quantized value. Our job is to find the error between this sample and the quantized version. So you need to exactly sample the input at this point itself, right? So this amplifier, we need to sample the, this thing has to sample the input during phi 1, right? And as we saw, we'll have multiple branches like this, and each of them will sample during the same phase, right? And this depends on how many bits you have here. If this is 3 bits, you have 8 branches, right? Is that okay? So now remember that this phi 1, phi 2 clocks, they are all generated on chip, and that has to be distributed throughout your design, right? So let's say phi 1 you generate somewhere here. So this goes to the ADC here, and then this has to go to each of these branches, right? Now, can you tell me if, can you comment on the relation between the clocks that the ADC receives here and the clock that is received by the switch here? Will they be identical, or will there be any mismatch between them? Sorry? So what kind of mismatch? Let's say the clock here is something like this. Okay, this is phi 1 we are generating here, and this has to be routed long, and it has to reach the first ADC, let us say. So obviously the generated clock will reach here after some delay. So which means the clock here also will have some different delay, right? So the point is, this might be the clock that is going to the ADC. Okay, but the actual clock that is going into the sampling switches in these branches, they will have different skews. For example, the first branch might receive the clock, say here, with this delay. The second branch can have a slightly different delay, right? Okay, so this will mean that we are not sampling the same input sample in all the branches, right? And this is particularly problematic if the input is also changing rapidly, right? That is, if you are designing a very high-speed ADC where you are trying to digitize fast changing inputs, then this is the actual time instant at which you are supposed to sample the input. But say the ADC is sampling here, but it can so happen that this switch here might sample the input at this point, right? And another branch can sample here and so on. So this will again introduce errors, right? So we are having a lot of errors here. So based on the discussions we have had in many classes, can you suggest some technique to correct for this? Okay, is that okay? The problem is arising because with different clock edges, we are sampling different inputs, and the input is also changing during this entire period, right? And that is why at different clock edges we are seeing different inputs. So we cannot avoid this delays in the clock. So what you do is you make sure that the input is not changing throughout the clock period. So what you do is you usually have a sample and hold. Okay, so the input might be varying fast here, but the output here might look like this. So this can then be given to our ADC here, and of course the switch capacitor branches. Sorry. Okay, let me draw in separate page. So you have a global sample and hold. So the input can be varying here, but the output will sort of remain constant. So the input sampled by the ADC and our switch capacitor branches, they'll all be same. Is that okay? Fine. So, okay, so now that we have seen how this can be designed in circuit level, let's start discussing how we can start designing this ADC. Okay, so say you are asked to design a 12-bit ADC using pipelining technique, and there are multiple ways, right? So one way is to have, have a 3-bit here, 4 plus 4 plus 4. So how many bits of resolution this will realize? I mean, what I say is this is the first ADC resolution, this is the second ADC resolution, and so on. And let's say I'm having 1 bit of redundancy in each stage. So what is the overall resolution? 12. Okay, this is 3, 6, 9, and 12. Okay, or I can also realize the 12-bit as just having a 7-bit, sorry, a 6-bit plus a 7-bit, right? So this is giving 6-bit. This will give an effective resolution of 6 bits, so total 12, right? So we have two choices. One is to have a long chain of low resolution ADCs or a shorter chain of high resolution ADCs, right? So just like our real life, we are having to make a choice between two, right? And if you're a rational person, what do? You find the pros and cons of each of the choice and see which is better, right? Or if you're a very rash person, you say, okay, I don't care, I'll just choose something randomly. So let's address, or look at these choices and see what are the cons in each, so that you can choose to be a rational designer if you want. Okay, so if you have this choice where you have a long chain of low resolution ADCs, what do you think can be the problem? Sorry? Sorry? Huh? What do you think can be a disadvantage with this choice? Sorry? Okay, more ADC. But here, okay. Yeah, number of comparisons is what needs to be compared, right? So this is not a proper comparison. Sorry? What do you mean by complex architecture? Okay, sorry. Yeah, that is one thing. We'll have more latency here. More stages, we'll have more latency. And also remember that we have 4 stages. How many residue amplifiers you need here? 3. And each of these residue amplifiers will introduce some gain error, and all of them must be corrected digitally, right? So that's going to kind of add more complexity when you're trying to do digital correction. So probably, gain error correction might be tricky here. So with this choice where you just have 2 states, but say high resolution ADC in each states, what do you think can be a problem? Again, you have to compare the total comparators here. It might not be straightforward. So is there something else? Or let's say come along that line. So if you have a 3-bit ADC and say a 7-bit ADC, which of them will provide a higher load to the preceding stage? And remember, this has to be driven by some stage, right? My input will be given to some buffer, and the buffer has to drive. So a 3-bit ADC or a 7-bit ADC, which of them will present a larger load to the preceding stage? Sorry, 7-bit, right? So the point is, when you have high resolution stage, that's going to load the preceding stage. Okay. And also, the moment you have a 7-bit ADC, how many DAC elements you need for 7-bit ADC? How many thermometer output ports will have? How many bits thermometer you will have? 127, right? So you need to have 127 capacitors, right? I mean, you remember, right? We had several switch capacitor branches, right? So now you need to have 127 capacitors. Again, you need to make sure they are properly matched. That's going to be a problem. And also, most importantly, when all the capacitors are transferring charge, you will have total of 127 capacitors loading the op-amp, right? Is that fine? So this will again increase the load seen by the op-amp here. So finally, you'll realize it using some GM. So if the capacitance load increases, what can you comment on the power? Sorry, if the capacitance load increases for the GM, what can you say about the power consumed by the OTA? It will increase, right? I mean, you have larger capacitor, you need to push in more current for the same voltage so that the voltage settles quickly, which means you need to have a higher GM. So this can in turn consume more power. Okay. So the bottom line is, there is no clear choice as to what is good, what is bad. You find out, you choose 2 choices and see which is good for you and do it. So that's what is done in practice. This is true with any circuit design, right? I mean, for an op-amp, you will have infinite ways to size the transistors. There is no one ideal solution. Right? But again, with respect to the input loading, it helps definitely. But now you are, let's say you are making it 2 bits. So I need to have, say, how many bits? 11 bits or something, right? So now I need to have 11-bit ADC, which means I'll have 2 power 11 DAC elements. So the loading on this op-amp will increase even further, right? So it's all a compromise. You have to choose something. Okay, so let's stop here and we'll continue from this next class.